So we've been discussing optimization techniques for finding solutions to various optimization problems. And so far, we've discussed two different algorithms. We've discussed the Newton-Raphson algorithm, and we have also discussed the gradient ascent or descent algorithm, right? In an effort to solve this particular problem where we want to obtain theta star such that it is the argument that maximizes the function f of theta. But both of these methods, Newton-Raphson and gradient ascent, imperatively involve derivatives. We have to take the derivatives of the function that has been provided to us. And in the Newton-Raphson's case, we have to have a second derivative. What if we're dealing with an objective function that is not differentiable? Or in general, what if we don't want to go and use sort of the derivative strategy for some reason? Now, I'm not saying that the algorithm, which is what I will introduce, does not involve derivatives, but what we'll learn is that it need not involve derivatives, okay? And so one method when we don't have a differentiable objective function, particularly, is to potentially construct an algorithm. So what is an algorithm? So again, consider obtaining a solution to the following problem, where we want theta star, which is the argument that maximizes some function f of theta. The minorized maximize algorithm, which is the algorithm, okay? What it does is at a current iterate, it finds what is called a minorizing function at that point, and then it maximizes that minorizing function. So just to understand, we're still in that framework where we're going to construct a sequence theta k with the hopes that as k increases, then theta k, should converge deterministically to my theta star. Right? This is what we're looking for. So in the Newton-Raphson algorithm, when we have a concave objective function, this holds true. We saw in the gradient ascent algorithm, if we choose our good starting values and good learning rates, we do have this hold true as well. Now, the question is, how do we actually implement this algorithm? Well, the idea is that we're going to find something called a minorizing function at any current iterate theta k, okay? And then we will maximize that minorizing function. So what is a minorizing function? A minorizing function is a function f tilde theta given theta k. So I just want to take a second to understand what this means. This is basically a function of theta that changes with theta k, right? So given a current different iterate, it will give you a different function, right? So given a certain value of theta k, it is a function as a function of theta, okay? A minorizing function is such that f theta k is equal to f tilde theta k given theta k, and f theta is greater than equal to f tilde theta given theta k. So let's actually take a closer look. So let's say this is my objective function, f of theta, okay? And this is the current value of theta k. Now, the minorizing function should satisfy two properties. It should satisfy this property and this property. The minorizing function will be denoted in red, and it will denote f tilde. That's the minorizing function. Now, the minorizing function is such that f theta k is exactly the same as f tilde theta k. Now, what is f theta k? It is this over here. That means the minorizing function f tilde theta passes through this point f tilde theta k. Okay, so the function will pass through this point for sure. Now, will it pass like this, like this, like this, like this? We don't know, but it will pass through this point. Okay. Now, further, at all other points, theta, so at every other point on the x-axis, right? At every other point on this axis, which characterizes theta, f theta, my objective function, will always be larger than or equal to f tilde theta given theta k, right? So it will always be greater than or equal to my minorizing function, which means the minorizing function lies below my objective function everywhere, but at theta k, it touches my objective function. So I want to construct a minorizing function, that looks something like this maybe. Okay, and then it can keep on going in some way. It might go on like this. This in red is my f tilde theta given theta k. Now the key point here is that it's given theta k. So if this is theta k, that's great. If this is theta k, right, then my objective function is still f theta, but my minorizing function could look something like this, right? Where it touches the function only at this point or at this point, and everywhere else the minorizing function is below my objective function. And I'm going to make such functions. I want to try to find a function that's minorizing. And then once I've found a minorizing function, my next iteration will be theta k plus 1 is going to be, the next iteration will be the argument that maximizes f tilde, the minorizing function. So in this particular case, this is where the maxima occurs. And so this value here would be theta k plus 1. If this was my theta k, and this is my minorizing function, then this minorizing function is maximized here. And so this value would be theta k plus 1. And in this way, we would keep moving and keep constructing, keep getting the next iteration. All right. Now, what's interesting is that, let me just clean this up a little bit. What's interesting is that this algorithm, the algorithm, actually has the ascent property. And what I mean by that is that every update increases the objective function value. So let's take a look again. So let's say I have my objective function over here. Okay. What this is saying is if I look at different thetas, okay, and if I look at different theta values, then at every iteration, it's going to keep climbing the objective function. At every iteration, it's going to keep climbing the objective function. It will not do something like this, that it's here once, and then it jumps to this value where the objective function is actually lower. Okay, it will not do something like that. So how do we show that this algorithm has the ascent property? Well, we can see this by first we have to understand what the ascent property is. So an algorithm will have the ascent property if f theta k plus 1, or the value of the objective function at the next iteration, is greater than or equal to f theta k. That's when it has the ascent property, right? Now the one way to show this is to say, well, let's look at what f theta k plus 1 looks like. And by construction of the minorizing function, I know that f theta k plus 1 is always larger than or equal to f tilde theta k plus 1 given theta, right? This is by definition of a minorizing function. Now, the other thing we note is that, well, f tilde theta k plus 1 is the thing that maximizes, is actually obtained by maximizing f tilde theta given theta k, right? That's how theta k plus 1 was obtained, which means f tilde theta k plus 1 given theta k is definitely greater than or equal to f tilde everywhere else, which includes theta k. So then this is by how theta k plus 1 was obtained, right? But now, going from here to here, this equality trivially holds again by definition of a minorizing function. So the minorizing part is truly critical for the ascent property, right? And so what this means is that we will be in the situation where wherever we are, we will always climb up the objective function until we can't potentially climb any more near it. Now, this algorithm still converges to a local maxima and not a global maxima. It isn't guaranteed to converge to a global maxima. Okay. Nonetheless, so this means that if we want to maximize f theta, we may find a minorizing function for it. If we can do that, and then repeatedly maximize it. So if we can find a minorizing function and have a technique to repeatedly maximize the minorizing function, then we have an MM algorithm. So the key really is to find such good minorizing functions that are relatively easy to maximize. Okay. Now, a note here is that if our goal is to minimize an objective function, so if we are in the situation where theta star is the argument that minimizes f of theta, right? If that's what we're working with, okay, then if it's a minimization problem, then what we do is we find a majorizing function and then minimize the majorizing function. So this is our objective function. We are somewhere here. We want to find a majorizing function and then minimize that majorizing function. Okay. So hopefully that sort of design is clear as to what would go on there. Okay. But the question really in a maximization problem is how to construct such minorizing functions. So what we need to do is somehow obtain a function that satisfies these two properties. Now this can typically be done by using some sort of inequalities. And the inequalities that are typically quite useful is Jensen's inequality, which we'll use in the next week's lectures. Cauchy-Schwarz inequality can be quite useful in arriving at minorizing functions. And also in general, arithmetic mean and geometric mean inequalities. So again, these are not inequalities that I'm going to go in a lot of detail because we're not looking at models which require them. But this is just to let you know that the key really is to look at inequalities and see if we can use them to construct minorizing functions. Okay. But one technique which we'll use immediately in the next example is to potentially use the remainder form of the Taylor series expansion to construct a minorizing function. So if I look at f of theta, then I can do a Taylor series expansion that exactly extrapolates f of theta into f theta k plus f prime theta k, theta minus theta k. That's the first order Taylor series, plus a second order term, but that's evaluated, that has the component f double prime z, where z is some constant between theta k and theta. And when I use this form of the Taylor series approximation, this is the remainder form, and hence there is exact equality. Okay, and that is because I'm saying there exists some constant z between theta k and theta for which this will hold exactly. Okay, now typically I don't know what z is, so I don't know what f double prime z is going to look like. However, if I have an objective function such that its second derivative is bounded below by L, right? So if we can lower bound f double prime z by L, then I can construct f tilde. So what I have is that this term over here is then greater than equal to L by 2 theta minus theta k squared. Okay? So I can then construct f tilde theta given theta k based on this term over here rather than this term over here. So I construct f tilde theta given theta k to be equal to f of theta k, which is this exact term, plus this exact term, plus this term, because that's what is going to give me the inequality. Okay, so if I look at this term over here, right, this equation, so the first thing I look at is what is f tilde theta k given theta k. Well, when I plug in theta k into this side, I get f of theta k, that's already a constant. The only place where theta shows up is here and here. But when it shows up here, I get theta k minus theta k, that's 0. Then it shows up here, I get theta k minus theta k again, which is 0. And so I finally get this is actually f theta k, which is exactly the first property that I want of a minorizing function. And the second property is already satisfied because of this inequality. So then this is a minorizing function. And this can only work if f double prime z is greater than L. Okay. And then because this minorizing function is nothing but a quadratic, I get the iterates, and the iterates are theta k plus 1 is equal to theta k minus f prime theta k divided by L. So what this is really doing, if you notice, this is very similar to a gradient descent, except, I have this particular term here rather than the plus 1 by, rather than the plus t term. So in some way, what this is doing is, this is an informed way of choosing the learning rate for gradient ascent. Okay, so if L, for example, is negative, so if there's no reason for L to be positive, so if L is less than 0, right, then what I have is, theta k, minus 1 by L, which is a negative number, so it becomes plus f prime theta k. Okay. This is what the next iteration is going to look like, and it basically gives you an informed way of choosing the learning rate for gradient descent. So let's actually look at the location Cauchy example. So for our location Cauchy example, remember we have the log likelihood, and I call the log likelihood is my objective function, which becomes f of mu. Then I get minus n log pi minus summation t going from 1 to n log 1 plus xi minus mu whole squared. This is the objective function, and I am aware, I know what the derivatives are. The first derivative is this, the second derivative is this. Okay, this allowed us to do the Newton-Raphson algorithm, but I know that this objective function is not concave, which means that I have a situation where Newton-Raphsons can diverge or converge to a local minima and really break down. I also saw that the gradient ascent algorithm for this objective function was a little sticky, because sometimes it wouldn't converge at all, sometimes it would basically oscillate, and sometimes it did work based on the learning rate. Okay? But I could also do what I did before, is I could do the whole Taylor series expansion, where I have f of mu equal to f of mu k plus f prime mu k, mu minus mu k, plus half f double prime mu k, mu minus mu k squared. Okay. Now, if I look at f double prime in general for any given mu, what I see is I have this function here, right? This is the second derivative. Now, in the second derivative, let's just look at this particular term here. If I can lower bound this particular term, then I can get a lower bound for f double prime mu. So I'm going to try and get a lower bound for the inside the summation term. So I have this term here. Now what I see is I have something positive minus 1 divided by this ratio. So naturally, if I'm adding something positive in the numerator, then this is greater than equal to if I were to not add something positive in the numerator, right? And so this term is greater than equal to 2 times minus 1 divided by this. That part's simple. But then I also notice, that this whole term over here is something, this term over here is basically minus 1 by 1 plus a, right? Now, that means that and a is some positive number. So the denominator is actually increasing in size, which means that this actually is going to be equal to greater than or equal to minus 1, right? Okay. So what I'm doing is I'm adding a positive number over here. So I'm increasing the size of the gradient, increasing the size of the denominator, which means that in general the number is getting smaller. However, because of the negative sign next to it, this number is turning out to then be greater than this number over here, right? Because of the negative sign next to it. So that means this whole expression over here is greater than or equal to minus 1. and I take it on the other side, so this becomes greater than or equal to minus 2, right? So this implies what I finally get is that if I take this number here and I plug it back here, I then get that f double prime mu is greater than or equal to minus 2n. Right? And if you notice, this number turns out to be negative, right? So then I finally get that f double prime mu is greater than or equal to minus 2n. So this is what I can use. So actually, this shouldn't be my L. This is my L. Okay, and I can take this L and basically run my algorithm as with using the fact that theta k plus 1 is equal to theta k minus 1 by L f prime theta k. And when I plug in all the necessary components, I get exactly these updates. Okay. Right. So hopefully this makes sense. And we'll see in the next R video that actually when you implement this, you get very fast convergence to the actual local maxima that's close to the value that you've started. But this is not really, I mean, it really helps to obtain sort of an automatically tuned learning rate. But often you're not going to be able to find the L, the lower bound. But more than that, a lot of the utility of the algorithm is for situations when you don't have the gradient vector available. Because if you have the gradient available, you can implement gradient ascent without much thought, without much sort of calculations to do, and it does become quite easy. So the question is, when can we use this? Or what are the examples where the gradient is not available for the objective function and we can use something like this? And our go-to example for that is going to be the bridge regression problem. Very similar to ridge regression, but now dealing with slightly tricky situations. So this is what we move on to our second example. Now, notice that this is now a multidimensional example because it's a regression problem. So recall ridge regression, which is something we did a few videos ago, and ridge regression was a particular case of penalized regression. So recall that the case of the penalized negative log likelihood problem during ridge regression, where we had the following objective function. We had q beta equal to this y minus x beta transpose y minus x beta by 2. This was our loss function, or this was basically our negative log likelihood. And this was our penalty term, right? And our goal was to find beta star or beta penalized by minimizing over the parameter space q beta, right? And so we turned it, recall, into a minimization problem because we were putting a penalty on the negative log likelihood. So we'd already taken the negative of the log likelihood and then put the penalty. Okay, but the thing I mentioned at the time as well, that this penalty function is a little arbitrary. You can choose a different penalty function and get different estimates of beta. So the world is your oyster based on the kind of penalty functions you might be interested in. By changing the penalty function, the above ridge regression objective function can then be generalized into something called bridge regression. And the particular kind of penalty function that works or that is of interest is this one, where QB beta is the same loss function, but the penalty function is now lambda by alpha summation I going from 1 to p, absolute value of beta I to the power alpha. So basically, if alpha is equal to 2, it's going to match this function exactly. Right? And the values of alpha that are considered are alpha between 1 and 2, and lambda has to be positive. Right? So when alpha is equal to 2, this is ridge regression. And when alpha is equal to 1, which is a very popular case, it becomes the popular lasso regression. Okay, so this is the general bridge regression problem. Now, different choices of alpha lead to different style of penalties and different styles of penalizations. And for a given value of lambda, what's happening is that when you fix a particular lambda, smaller values of alpha push the estimates closer and closer towards 0. Okay, because you basically are penalizing larger values. You're penalizing larger values of beta because you're taking sort of your smaller values of alpha are really pushing the weight down smaller and smaller, right? It's taking large values of beta and really pushing them down. Okay. Okay. What we need to do is find the bridge regression estimates, which is again argument that minimizes QB of beta. Okay, so this is our problem that is of interest to us. This is our objective function. Again, I'd like to mention here that in general, in this course, we are not really looking at the regression problem. We're not really looking at what sort of modeling choices go into choosing alpha and lambda necessarily from a statistical perspective, but rather we're just looking at the computational hurdles and actually finding solutions to this and to this. Okay, but why is bridge regression interesting or useful or helpful is not something that's the focus of this course. I just like to mention that. Okay, now immediately what you notice is that if I want to minimize this function, well, I have this part which is easy to deal with, right? It's a quadratic. This part that is not so easy to deal with because of the absolute value. So y minus x beta transpose y minus beta is a convex function and it's well behaved. This part, the second function, is not well behaved in the sense that it is not differentiable, but it is convex for alpha greater than equal to 1, right? So for example, the absolute value looks something like this. That is a convex function. For alpha equal to 2, this looks like something like this. That is a convex function. Which means both these functions are convex functions. And since the sum of positive convex functions is convex, the objective function is overall convex. So in fact, we don't have to go and do fancy Hessian tricks to understand whether we have a convex function or not. This is a linear combination or sum of two positive convex functions, so that means it will be convex. Thus, our optimization algorithm is expected to converge to a global minima, right? Again, this is a minimization problem. So it looks something like this, and we will expect something like Newton-Raphson, etc., to converge to this minima, except we can't implement Newton-Raphson because my objective function has this non-differentiable part. Okay. So for alpha equal to 1, the objective function is not differentiable at 0, right? Because of the absolute value. And for alpha, in 1 and 2, the function is actually not twice differentiable at 0. So even if you could get the first derivative, you can't really get the second derivative for any value of alpha. So using Newton-Raphson and even gradient descent here is not going to be possible in general if we're opening up to all values of alpha. And so instead, we can use an algorithm here. Now, since this is a minimization problem, it's not a maximization problem, we are not going to construct a minorizing function. It's a minimization problem, so we're going to construct a majorizing function and then minimize that majorizing function. That means this is our objective function. We are going to construct at a particular value of theta. We're going to construct a majorizing function here and then minimize that majorizing function like this. Like this. Okay. It's still called the algorithm, coincidentally. Okay. So what we have to do is we have to find a majorizing function that upper bounds QB beta, right? We have to find something that upper bounds and then minorize the majorizing function. Okay. This is what we have to do. Intuitively, though, we know that optimizing the majorizing function will again require derivatives of the majorizing function, right? So what I'm trying to say now is if we are going to construct a function that majorizes this, which means that it sort of looks something like this, right? Then I need to be able to find the optima of the majorizing function, which means I would like to take a derivative of the majorizing function and set it to 0 and see if there's a known solution, an analytical solution of the majorizing function so that I can do the steps of the algorithm. Which means that my majorizing function is expected to then be differentiable. because I do want to take a derivative of some function and set it to 0. This is the logic. So intuitively, optimizing the majorizing function will again require derivatives of this function. Thus, our goal is to find a majorizing function that does not contain an absolute value and is thus differentiable. Okay. So we have two components of our QB beta. Right? One component is y minus x beta transpose y minus x beta by 2. Another component is lambda by alpha, summation I going from 1 to p, beta I to the power alpha. I want to construct a majorizing function, but the only part of this that's non-differentiable and has absolute value is this part. So if I can bound this particular function and remove it with some functions that's both differentiable and such a way that it actually becomes a majorizing function, that's what I want to do. And I don't really want to mess with this because this is very nicely differentiable and very well behaved. So further, y minus x beta transpose y minus x beta, this term is well behaved, differentiable, and quadratic. Right? So I don't really want to mess around with it. I can keep that term in the majorizing function. Instead, we would like to lower bound this particular function. If I can lower bound this particular function, then I'm going to get something that this term is greater than or equal to something else, which means I have myself a majorizing function. Okay, so in general, so now this argument is going to be a little bit tricky potentially to understand, so stick with me. In general, we are going to consider a function h of u, which is u to the power alpha by 2 for u greater than or equal to 0. Okay, so I've sort of stopped worrying about this. Just refresh your brain and just consider function h of u, which is u to the power alpha by 2 for some u that is positive. Now for this function h of u, let's take the first derivative. And h prime u is equal to alpha by 2 u to the power alpha by 2 minus 1. Right? That's the first derivative. So u by 2 comes here and I get a minus over here. I can take another derivative to find the second derivative of h double prime u, and that is alpha by 2 times alpha by 2 minus 1 times u to the power alpha by 2 minus 2. Okay? Now, if I consider alpha between 1 and 2, well, this value is always positive, this is positive, but when alpha is between 1 and 2, this is negative. Right? So h prime u is then always going to be less than or equal to 0. Because h prime u is always going to be less than or equal to 0, I find that h of u is a concave function, which means it's a function that looks like this. Right? So that's easy to see. But for a concave function, so if I look at this, for a concave function, the first order Taylor series and the rooftop theorem together say the following, that the first order Taylor series creates a tangent line that is above the function. What this is saying is that if I have a concave function and at anywhere, if I'm going to draw a tangent line, then that tangent line anywhere lies above the function. There is no place where it cuts and goes below the function. Okay, so this is what the rooftop theorem says, and you can see this just by visual. Right, you create a concave function and you try to draw a line, a first order Taylor series expansion, which is a line that does not always lie above the function, and you won't be able to do it. So thus, for a u star, if I consider a first order Taylor series expansion of h of u around u star, what's going to happen is if I look at the first order Taylor series expansion, which is this, h of u star plus h prime u star, u minus u star. Well, h of u, my function h of u, is always going to be equal to less than that Taylor series expansion around any u star, right? But now I can plug in what h prime looks like. So I get this is equal to h of u star, alpha by 2 u star to the power alpha by 2 minus 1, u minus u star. Okay. Now, I seem to be going on a completely different tangent, but I'm not. I considered this function h of u to begin with for a particular reason. What I've done so far in these steps is I've constructed a function h of u that looks like this, and I have constructed an upper bound for that function. Okay, an upper bound that is differentiable as well. So this is what I'm going to use to construct a bound for my optimization problem. For any given iteration of the optimization algorithm, we are given a beta k. Okay. Now taking u over here to be beta I squared and u star, the point where I'm taking a Taylor series expansion, to be the current iterate beta k and the ith component. So just to be clear, beta I, so beta, the vector beta is beta 1, beta 2 up to beta p. So when I say beta I am talking about any ith row, and beta k is the current vector, which is beta 1 comma k going up to beta p comma k. Right? So when I say beta I comma k, I'm talking about any ith component in this vector of betas. So now in this inequality, this side and this side, I'm going to plug in u star and u. So h of u is nothing but absolute value of beta I by alpha, and that's based on what h of u is and what u I'm considering. Okay. H of u is equal to this. This is less than equal to h of u star, which is absolute value of beta I k to the power alpha, plus alpha by 2. Then I plug in what u star is, so it's this thing, to the power alpha minus 2, beta I squared minus beta I k squared. Okay. Right? Now, what I do is I can multiply this with this, so that squared combines over here. So that just gives me alpha by 2 beta I k. And I get a beta I squared separate, so I get beta I squared times this constant. What's interesting now is that these things are just dependent on beta ik, which is my current iteration, which I know is just a constant, right? It's not a function of the actual betas. So this is some constant, plus mik by 2, where mik I denote by this, right? Where mik is alpha beta ik to the power alpha by minus 2. Okay. So what I've done now is basically, if you just look at this thing over here, and if you look at this less than equal to, and you look at this over here, what I have finally is that I've taken beta I to the power alpha and written it less than equal to some constant that we can worry about or not, plus mik by 2 beta I squared. And this is the upper bound that we have gotten based on this rooftop theorem and this whole H construction for the part that, for the part which was not differentiable. Because I've gotten that upper bound, and if I plug in beta ik in this equation, I get this cancel with this, and I only get back this. So in fact, it is a minorizing function, or majorizing function in this case. So now that we have this upper bound and the penalty on the penalty function, we have an upper bound on the full objective function, because I can just take this and plug it back. So the objective function can be bounded above by qb beta is less than equal to some constants, and I don't need to know the constant, I'll tell you why. Constants plus this part that was well behaved, plus this summation j going from 1 to p, mjk beta j squared lambda by 2 alpha, and that is when I just plug this back. So I have constructed now using this an actual objective function, a majorizing function for my objective function. So this is my majorizing function. Okay. Now, why is this upper bound useful? What do I do with this? Well, remember that at any given iteration, the optimization is with respect to beta. Thus, the constants are actually truly constants. So what I mean by that is that yes, there are constants over here that have absolute values, but I'm not taking derivatives with respect to these beta k's. I'll be taking derivatives with respect to beta I, which is only present here in a quadratic form. Okay. So the constants are truly constants. The upper bound has no absolute values and is easily differentiable, right? Recall that we obtained the upper bound function using a derivative of h of u. This derivative is actually not defined at u equals 0. However, the derivative of h of u was only being utilized actually at h prime u star, where u star was only my current iterates of where I will be, right? So as long as, because we're using the derivative function at u star equals beta I k square, which is the previous iteration, so as long as we do not start at 0, this upper bound is valid. Okay. If we start at 0, then beta I0 will be 0, and then I won't actually be able to go ahead and do what I just did. Finally, the upper bound is easily optimizable as it is similar to ridge regression, and we'll see what we're talking about. So if I look at my objective function here, now what does it look like? It is beta j squared. There's another constant over here, and there's some number over here. But it basically looks very similar to y minus x beta transpose y minus x beta by 2 plus lambda by 2 summation beta j squared, which is what we used to have in ridge regression. Except now there's some number here and some number here. But, and I'll leave this up as homework for you, it should be straightforward to see that actually you can take the derivatives and set to 0, okay, and show for yourself that actually finding the optima or finding where this function is minimized is a one-step process with an exact solution that looks something like this. So the objective function is similar to ridge regression, except that it is weighted. If you follow the same steps as in the ridge optimization, you can show that the minimum actually occurs at beta k plus 1 equal to x transpose x plus lambda mk inverse x transpose y, where in ridge regression, this mk thing was not there. We just had lambda. Now we have this mk, where mk is a diagonal matrix of all the small m's by alpha. Okay. And it is this mk over here that contains information about the previous beta k. Nothing else contains information about the previous beta k, right? So these mk's exactly is what knows what's going on and which direction to actually go towards. Okay. So in this particular code, I generate data from a particular linear regression type model. Okay, and this is something we've seen before. And then so what I do is I generate synthetic data, which we're already familiar with y equals x beta star plus epsilon. Epsilon's from this distribution. Beta is some ground truth chosen for generating the data. And what we'll do in the code is we'll look at MLE, ridge, and bridge estimates for various values of alpha using a particular given value of lambda. Okay, so exactly how the code works, we'll go over in the next video when I show you the actual code, and we'll actually go through some of these tables as well. Okay, what I would like you to do, although when you see the code, is what happens if you were to start from 0, because I've warned you against that. And also what happens if you try changing the values of the penalization term lambda. So give a go at that and see if it has any impact. Okay. The questions that you should think about also is how should we choose alpha for a given modeling problem? How should we choose lambda for a given modeling problem? And will algorithm always converge to a global maxima in general for any objective function? Now these two actually we will address very soon, maybe in week 11, most likely, or maybe week 10. And this one, I really want you to think about is it guaranteed to converge to a global maxima for a non-concave objective function?